Welcome to the fourth lecture of this NKB lecture series. In this lecture, I think we will be applying Kg equation to particle moving under the action of a Coulombian force. This topic, in fact, is divided into the two lectures. This lecture, the fourth lecture, and the next, the fifth lecture, because it's a little lengthy. So I have divided it into two parts. At least in this first part, we will be first discussing how the differential equation, second order differential equation, will be solved using the series solution technique. And once we will develop the recurrence relation, and at the end of this lecture, in the next lecture, we will solve that recurrence relation to unravel the physics of this topic. So basically, it is the application of Kg equation to a charged particle moving under the action of Coulombian force that we try to describe. So welcome you all. So welcome back, friends. We start with application of Kg equation. So as a first application, that we can apply this Kg equation to a particle which is under the action of a Coulombian force. In fact, the equation which we have derived, it was for the free particle. So for the free particle, if we just recollect, equation which we have derived was like this: Nebula square minus 1 by c square del square by del t square psi rt is equals to your m0 c square by h cut square psi rt. Correct? So this was the equation that we have derived for a free particle, and its interpretation, the difficulty in explaining the negative probability, negative charge energy, that we have understood by assuming not the probability as a position probability, but by assuming that as the charge, multiplying probability by the charge, we can interpret it as the electric charge probability. But a more insight is available when we consider that a particle is interacting, not free. So basically, now we have another case where the particle is allowed to interact. And whenever we allow the particles to interact, so apart from its kinetic energy, now the potential energy will also contribute to the total energy. So as a simple case, we assume that a particle is interacting through Coulomb field or the Coulomb potential. So basically, the topic which we are trying to learn is that particle is under the action of Coulombian force. So particle in a Coulomb field. To picturize this concept, we take the example of hydrogen like problem. Right? So I have a situation where z number of protons with positive charge, which are located at the center of it. So it's a positive proton, and in the outer orbit, a charged particle is moving. So this is my negatively charged particle which is moving at some distance, which we call as the radius of this circular orbit. So I denote it as rho r0, for example. So scenario is this, that this particle, the negatively charged particle, is experiencing Coulombian force and it is moving relativistically high. So we employ now Kg equation to explain this, explain the physics of this part. Now, as I just said, that when particle is also under the action of potential, so its kinetic energy, say c square p square, relativistic kinetic energy, which we have written. Again, all the terms are familiar to you. m0 is the rest mass of a particle, p the linear momentum. This kinetic energy will no longer be the total energy. So instead of this as the total energy, now total energy will be subtracted by the potential. So if I write the potential as a V as a function of R, let us also assume that it is a time independent problem, then the kinetic energy will be the total energy minus potential energy, or in other way you can say the kinetic energy plus potential energy is the total energy. This, if I call as now E dash, for example, then using this equation, we are now writing the expression for a particle which is under the action of Coulombian field. And in our case, this V of R is in fact, because it is a Coulombian potential, 1 upon R potential. So it will be only radial part or R dependent part, which we can write as if Ze number of positive charge at the center, and if the equal amount of charge, let me assume the charge of this particle is also E but negative, then what we have Z E square by 4 pi epsilon 0, and since it is a positive and negative charges, so it is attractive. So this negative sign indicates the attractive potential. So we have now VR ready, the relativistic kinetic energy is there, so we can now write the, again similar to this as we have written for the free particle, now we write the Kg equation for the interaction particle. So my Kg equation in this case will be written like this: IH cut del by del T, that is the energy part, E which I have written here as an operator, V I can write as an operator, minus, but because V itself is having minus sign, so this potential part will contribute like this: Ze square upon this 4 pi epsilon 0 R, correct? And then I write this kinetic energy, this is the square of kinetic energy, correct? So C square P square M0 C raised to 4, which we have already derived. So this part I can write here, and of course my function psi RT, and then this total energy and potential energy that gives me the kinetic energy, so which I will write directly C square, and again for P square I use the operator correspondence, so it is H cut square nebula square plus M0 square C raised to 4, and of course this is operated on psi. So this is my Kg equation for a particle who is interacting through Coulombian potential, correct? So this is the expression which we need to solve. We also know that here the potential which we have considered, the Coulombian potential, it is time independent. And because of this time independent nature, it allows us to separate your psi into two parts. It is always the property of the interaction Hamiltonian or the potential to determine the nature of the wave function or the nature of the solution. So this we can separate. But this separation is possible only because your potential does not involve time. But if it does, then in that case, such a separation is not possible. So to start this equation, to start this solution, because of time independent character of VR allowed us to separate this psi. So I now go with this separation of variable method. I separate my psi into two parts, R dependent part and the time dependent part. So I can write my psi, the wave function describing a particle, into two parts, that is only R dependent part, and then I multiply the time independent part, which I can write as minus I E T by H cut. In other fashion, you can also write, the E by H cut, H cut omega is E. So this can also be written as, it is equivalent, in fact, psi of R into E raised to minus I omega T, where omega is the angular frequency. So this I can substitute back to my equation. Let me just give you that equation back. So this is my IH cut. I just forget, it is a E dash square that I am writing, correct? So if I write the squaring of this is the equation which we should consider. So this square, this equation which we are now solving, correct? So let me substitute this all information. So my expression will look like this. Let me write it again. So my IH cut del by del T plus the potential part, that is Z square by 4 pi epsilon R whole square equals to the kinetic energy whole square term, correct? So it will be your, again, in operator form, if I write, it will be minus C square H cut square nebula square plus m0 square c raised to 4, and of course psi on both sides. And then I write psi in a splitted form, r and time dependent, and then I open up this part. I open up, so it will be your IH cut. It's like a plus b whole square type of thing, but this is a 2 times differentiation, so it is del square by del t square. Then there is like a middle term, so 2 IH cut Z square by 4 pi epsilon R del by del t, and the square of this term, so it will be Z square upon 4 pi epsilon R whole square. And then psi I write into 2 part, that is R dependent part, and there is a time factor like this. I prefer to write in this fashion because ultimately my goal is to find energy. So I write like this, IET by H cut. And obviously on a right hand side, the same thing I will do, C square H cut square, and let me write first nebula square m0 square c raised to 4 operates on psi, which is again splitted into 2 parts. Right? So this is the part which this is the thing which we will be doing. On the left side, we know that this term, entire term, is involving the time factor. Correct? So this exponential part will only be differentiated. So considering that fact, when I just open up this bracket, del square by del t square when operates here, so 2 times, so it is minus I e by h cut will appear 2 times. With this, it will appear once, where for this part it will be as it is. Correct? And in after operating this del by del t once or even twice, then exponential term will come again. So on the left side, throughout, this exponential term will be, even after differentiation, will be received. Whereas on right hand side, you can see there is no time factor. This nebula square is a space dependent part, and therefore there is no time factor. So from both sides, even after doing this differentiation, this exponential term will be common on both sides. So that in the next step we can cancel out. So when I do this calculation, this is appearing 2 times, minus IE by h cut appearing 2 times. So it is a minus I square or E square by h cut square and so on. Sorry friends. So this I can write, and this IH cut square is also there. So when I do this simplification, what I get on left hand side is h cut square E square, h cut square because of this, another h cut square which comes here. So it will be like this. So I do this one time when I do IH cut, and this minus I will make it plus. So it will be plus 2E. Rest everything is as it is. So it will be Z square by 4 pi epsilon 0 into R. And this is, there is no derivative involved. So it will be as it is, Z square by 4 pi epsilon R whole square. And as I've said, even after the differentiation, this exponential term will be received back, which in next step I will cancel out from both the sides. Whereas right hand side will be carry forward as it is, because as such it is not involving any exponential factor. So what happens that now this exponential term from both the sides are cancel out. And what you are left with is only this part, and you know that this is something like your Even h cut square when cancel out, it is like a plus b whole square type of thing. So what we have in the short, we'll have e plus, it is the square of this part, so it will be z square by 4 pi epsilon r whole square psi as a function of r only, and on the right side we have minus c square h cut square nebula square plus m0 m0 square c raised to 4 and psi of r. This equation, as you can see, does not involve any time factor, and therefore this is independent of time. It is taken care by the differentiation, and it gives the contribution like this. So basically, this is the equation we are now solving. Again, we go and look at the potential which is involved here. You know that this potential depends as 1 by r. It is not depending on the r vector. So it is only the radial part, or depends only on the distance, not on the angular part. And since there are no angular part involved, there is no theta and phi. And if no theta and phi, no angular part, so it allows us even to separate this nebula square term and your psi r into two parts. So because of this nature of the interaction potential, we can further apply the method of separation, and we can write my psi of r into two part, one which depends only on r, we call the radial part, and another part which depends on theta and phi. But since it depends only on r, only the radius is important, so it is having a spherical symmetry, and therefore for such a spherical symmetric potential or the interaction, usually this theta phi part of the wave function is described by what we call as the angular spherical part, which is your ylm theta phi. Correct? So basically this is your spherical harmonics that we can write. So this property of the interaction has allowed us to further split this psi of r as r radial dependent part and the theta dependent part. So this I will substitute back to this. I will also write the expression for the nebula square in terms of r part and the angular part theta phi part, and then I do some simplification. Then what I'll be able to obtain is a radial equation for a particle under the action of Coulombian force. So I go next to derive this. I substitute that part, radial and the theta phi part. So let me write that equation. E plus that left side will be in fact as it is, z square by 4 pi epsilon r whole square, and then I write r of r, y theta phi, and the quantum numbers which are involved I can write as ylm theta phi. And for nebula square, we know that where nebula square can be written into two parts, that is 1 by r square del by del r. This is the expression which you would recollect, r square del by del r radial part. Then we have 1 plus r square sine theta del by del theta sine theta del by del theta plus 1 by r square sine square theta del square by del phi square. Except this 1 by r square, which is common in last two terms, the remaining part is your minus L square by h cut square. So the same thing I can write like this, r square, but now you know that this r part and theta part, phi part are totally differentiated, totally separated. So instead of this partial derivative, I can write now it is a full derivative. So basically I have separated my r dependent part, and this, as I've said, except this 1 by r square, remaining is your L square by h cut square. Don't forget, this is nothing but your angular momentum operator, square of angular momentum operator. Correct? So basically instead of nebula square on right side, we can substitute this information. So if I go back to this c square h cut square, correct, and instead of this c square h this nebula square term, I can substitute this part. It will be 1 by r square d by dr r square d by dr, correct, and this part I write 1 by r square L square by h cut square. So this is my first term, and plus the second term, and everything psi and everything will be this. So basically I have used this property of nebula square and substituted here, and only thing which is now left that I have to simplify it. And for that I just remember that whenever L square operates on YLM theta phi, it gives us L into L plus 1 by h cut square, correct? So this L square when operates gives me like this, and of course YLM theta phi part will be recovered back. So I use this information here and I open up this equation, and this 1 by c square h cut square for simplification I take on a left side, and then you know that even your angular part L square operates on YLM theta phi. After that a YLM theta phi part comes back. So from all the term from left side and from both the terms on right hand side, this YLM theta phi part will cancel out. So I'm not writing now YLM theta phi part after operating this. So what I'll get, this c square by h cut square which I have taken on left side along with the minus sign. So what I have 1 by c square h cut square, this part will be as it is e plus z square upon 4 pi epsilon 0 r whole square, and as I've said that YLM theta phi part will be cancelled out from both sides. What I'm writing is this 1 by r square d by dr r square, and now this d of r by r, this and YLM theta phi is gone. This second term which I will be writing, L square is already operated, so it will give me L into L plus 1, correct, and there is already 1 by h cut square, and 1 h cut square comes in the numerator, so it is gone. So what you have L into L plus 1 by r square, you are left with capital R function, and that last term which will be coming as it is, so m0 square, don't forget the last term was m0 square c raised to 4, just to remind you, correct, m0 square c raised to 4. But since I have taken c square h cut square common, so here h cut square will come in the denominator and there is a reduction of the power. So what I'll write here is m0 square c square upon h cut square and your function capital R. This is nothing but your radial Schrodinger equation. You can see there is nowhere theta phi part in it. So this equation is known as the radial KG equation or radial relativistic equation. It is similar to what we have obtained for the ordinary hydrogen atom. Only this term is extra, correct? Because this m0 square series square term is not there when we consider the non-relativistic case. So this is only the extra term which appears here. And in order to write it in a specific form or a required form, so what I do, I write this part on the left side, and this I'll take on the right hand side. Just it is rearranging, there is no physics in it. So I just take it on this side and I just rewrite this to get the specific final form, correct? So I write just by rearrangement of this term, and then that term L into L plus 1 upon R square R of R. And then what we do here, this term which comes here positive, which I will write first. So it will be m0 square c square by h cut square, and then this term will be as it is. It is just the specific form which I am looking for, so I am just rearranging. So this is, as I've just said, is nothing but your radial equation. And therefore now we are looking for the solution of this radial equation. It is quite obvious if I take this d by dr inside, when it operates, ultimately it gives me the second order equation. So basically this is your second order linear differential equation which I want to solve. So the next exercise is to solve the radial Schrodinger equation, which is nothing but your second order linear differential equation. In order to do that, the common practice, and it is also required, that we must first convert this radial Schrodinger equation into dimensionless form. And the purpose is very simple, because such a different second order linear differential equations are already solved in the mathematics. So we can directly adopt the ready-made solution which is available for such a radial Schrodinger, such a radial equations or such a differential equations. But in the mathematics, the problem, the equations which are solved, they are in the dimensionless form. Whereas here, this physical quantities which are involved have a dimension. And therefore, in order to adopt directly the solutions from the mathematics encyclopedia, we have to convert this equation into dimensionless form. And this is a very common practice. So before we jump into the solution of this, let us first write the dimensionless form of this. And for that, now I define the variables or the parameters. I take, say, rho as a dimensionless. So this is my dimensionless parameter, right, which I define as alpha. If you need this rho to be dimensionless, no need to say your alpha must be the dimension of distance inverse or the meter inverse. So basically this alpha is having meter inverse in it. It is defined as, if I write like this, your alpha square is defined like 4 m0 square c raised to 4 minus e square upon c square h cut square. There is no rocket science in it. You can see it is nothing but, if I just open up this bracket, you can see that here it is a whole square term. So it is e square which is coming, correct? There is a 1 by c square h cut square. So basically this e square by c h cut square is like that, correct? So m0 square c raised to 4 minus this term I am taking as alpha square, correct? In fact, alpha will have a 2 factor and the square root of this, that we will see later on. So if I take alpha square like this, its dimension, the dimension of alpha will be meter inverse. Similarly, I define another parameter, let's say lambda. Then this lambda will be written as z square by 4 pi epsilon into ch cut. Again, this is also nothing but available directly from here. If I take this c square by h cut square inside, correct, then in the last term z square by 4 pi epsilon 0 r, this c and h cut will come because it is already square. So when I take it in, it will be only c and h cut goes in. So z square by 4 pi epsilon along with this ch cut I take as lambda, not r. So basically this I can call as a gamma, correct? So this gamma I can write as z square by 4 pi epsilon 0, 4 pi epsilon 0 ch cut. And similarly, I define now another parameter, say lambda, that is 2e gamma, this term, upon ch cut alpha. So this is just in order to convert our previous, this radial Schrodinger equation into the dimensionless form. We have assumed certain thing like rho, which is dimensionless, written as alpha, where alpha square is this, gamma and lambda. And when I substitute all this equation, all this part into the radial Schrodinger equation, and if I do some simplification, finally what I will get is the entire equation in the dimensionless form in terms of rho. So that I will write directly. So I just give you this as a simple exercise at home. You all can try, right, to how to obtain by substituting this information into this Radial-Schrodinger equation and then try to obtain this final equation which we will be using. Right? This lambda by rho minus 1 by 4, all this factor which is available we can write, correct? So I am directly copying, but I expect that you will all do at home, correct? So this is my, you can say the starting equation. It is nothing but a radial equation, but it is all written now in terms of dimensionless. Again, you can see this is the same equation analogous to your hydrogen atom problem. Who those have solved this hydrogen atom problem with non-relativistic formalism, then this is analogous to your hydrogen atom problem. It's like hydrogen atom equation. Only difference is there that instead of there L into L plus 1, now we have a presence of gamma square. Correct? This part appears only different. Otherwise, it is having the same nature, and therefore the methodology and the solutions which we are looking for will also have the similarity of the hydrogen atom in the case of non-relativistic part. So just it looks similar to our hydrogen atom problem. What I do now, instead of that, say L into L plus 1 minus gamma square, I may call it as a S into S plus 1. So that it looks like our same case. So this substitution will actually give me exactly, mathematically, exactly the same equation which we have obtained for hydrogen atom under the non-relativistic case. Correct? It is same mathematically, there is no change as such, and this is what we write. So my procedure of calculation will also go in a similar way. This is as it is the same equation, so I call it as a A dash. Correct? And then of course I do some further simplification. I can take this d by d rho inside, so it will be operated. Again I apply the chain rule of differentiation, keeping the one term constant, differentiate the second plus the other way around, and when I do this simplification, so what again I finally give that I am writing. So what I'll write after doing this differentiation, in the second term there is no as such differentiation, it is only this first term that I will do, but when after doing differentiation there is some mixing with this part, so that I'll write, and rho square I can take throughout common, and I do some simplification. So what I get is d square rho by d rho square. It's basically a second order linear differential equation which I will obtain, so that I write directly. Right? And then all the terms with r that I write lambda by rho minus this s into s plus 1 upon rho square, of course capital R, and then that term I deliberately write separately. It can be merged with this, but I write separately to show certain things. So this is the same equation, but only this d by d rho is now operated inside. And then this is the equation which is important in a sense that based on that we can cast our solution, we can design our solution. See, in the mathematics, while solving the second order linear differential equations, there are different techniques. Like you can talk about the Wronskian method, or the simplest one is the series solution method. So here also we are going to adopt the series solution technique to solve this second order linear differential equation. So the method which I am going to use is series solution. But in order to develop this series, in order to generate this series and to proceed further, it is required to know certain behavior characteristics of the series. And therefore, this equation is in a sense is the basic equation to design your series, which kind of series you can adopt to find the solution of it. And for that, we now focus on this equation at a rho which is very large. In the language of quantum mechanics, I can call it as a asymptotic behavior. So when your rho is very large, as per this equation, when rho is large, so ultimately I am talking about the very large distance r. So basically I'm looking for a solution which is allowed asymptotically. So when your R is very large and therefore your rho is very large, then obviously we just focus on this equation. Is this term is very large, rho is very large, so obviously this part will not contribute. Please don't mix up with this d rho and d rho square with rho. This is indicating the small change in rho at a given point, where this rho indicates the value of rho. So as rho is large, this term having rho in the denominator will contribute 0. This is also having denominator, so it is also negligible. And in fact, this is rho square, so it is a very large, and therefore this term will contribute almost 0. So at a large distance, only this part, the last term, will contribute. So the asymptotic solution of this equation B is like this, which I am writing. So d square by d rho when very large, all other terms having rho or rho square in the denominator contributes negligible, then what I can have is this equation. So this is the asymptotic solution of your equation number B. And you know that this is something like d square y by dx square plus or minus some number, some constant y equals to 0. And therefore, the solution of this equation when your rho is very large can be written something like exponential. It can be plus or minus. I can write this like a omega square. So square root of it I write as a solution. So it is like this. So behavior of this R, capital R function at a very large rho will be this. This is known as the asymptotic behavior of the wave function, radial function, like this. Mathematically, both plus or minus signs are allowed, but we know that if we assume plus sign, then as rho increases, exponentially this part increases, so your R will increase. And as R increases, R multiplied by y theta gives you the psi increases. And as psi increases, mod psi square, that is the probability of finding particle at a large distance, increases, which is against our intuition. It is against our expectation, because we have considered that the particle which is under the action of the, say, Coulombian force, it must be close to the nucleus. It should be close to the positive charge. You can't expect this charge E, negative charge, to be found at an infinite distance. So it must be found close enough to this. So asymptotically, the probability of finding particle should be 0, which is violated if I consider the positive sign. So this possibility, though mathematically allowed, is been rejected. And therefore, the only acceptable solution is with the negative sign. If I consider negative sign, as rho increases, your R decreases and probability of finding particle will become 0 at the large distance. So the permissible, admissible solution at an asymptotic level is that your R behaves like a e raised to minus half rho. Right? So we are now in a position to decide that our series which we are looking for must have the exponential factor with a negative sign, which behaves like a damping, and therefore the probability point of view we will be correct. And therefore, now from this understanding, the general solution, the solution, when I say solution, basically I'm looking for the mathematical expression for the R, radial part, should be like this. It has this form, e raised to minus half rho, which ensures your probability becoming 0 at a large distance. But for other region, for a finite rho, the equation is decided by this part. So this is the part which takes care of the finite R. Or we know that we have written everything in terms of dimensionless quantity rho. So this is the part which takes care of this. So now my exercise is turned, instead of finding r directly, if I know what is the f function, then multiplying f function with this vector, I am able to calculate r. So what is happening? That again, in order to solve this equation number b, which is the radial equation, correct, we are employing series solution technique, where this asymptotic behavior demands that your capital R function should have a factor like e raised to minus half rho, and for the other part, for other regions, for a finite value of rho, this function f is employed. So I now in the next step will substitute this r as a f into e raised to minus half rho in this equation, and I simplify. Correct? So again, it's a simple exercise. You are doing the 2-time differentiation here. Just look at this part. So d square r by d rho square. So when I do the 2-time differentiation, there are two functions. So one function constant, other will be differentiated, plus other way around. So this happens 2 times. So in the first, where you are doing differentiation twice, you will generate 2 into 2, 2 plus 2, that is the 4 terms. Here you will generate 2 terms. So likewise, you do the substitution and simplify. And again, I believe in you and I assume that you all will enjoy this. What you finally get is a very small, sweet and small equation like this. So finally, this substitution gives you the mathematical equation to be further used as like this. It's lambda by rho, and I have written this f function common. No need to say, because it involves exponential function. So even when you do the differentiation 1 time, 2 time, or constantly, this exponential term will come out as it is every time, and therefore what we get is the common f rho, and therefore we get this equation. So this is my equation number C. That is the next important equation to be solved. And you can see this equation looks very simple and we can manage it. As I've already said, we are employing the series solution technique. And in the series solution technique, now this function f I can write like this. I assume the series like a power series. Your variable is rho, so it is rho raised to some power, let us say s plus 1. Usually this is decided by, say, experienced guess that what kind of series you can adopt. This is you can also consider as a limitation, that who those are pioneering in this, they may have some difficulty in considering the type of series. But let us assume that this is the way we can solve. And of course, this part takes care of the other terms. So 0 is again a series, power series. So that I can write. And we know that it is a series. So obviously the summation will go. Let us say k is the variable to do the summation. It goes from 0 to infinite. Practically it's an infinite series. This is the coefficient to be determined. And again it's a power series. So I can write like this. And of course, in order to produce this series, to continue this series, at least the first member of the series, the lowest power of k, which is 0, the coefficient of that term should not be 0. At least to start, to initiate the series, we need the first coefficient should be non-zero. And then we will just go on putting this. So we assume that the series representing my function f can be written like this. Correct? So again, we have the same exercise. What we do, I use this f rho, put the value in the equation number C, and I simplify it. Again, this is the second time differentiation. So when I do the 2-time differentiation, I open up everything. First time, this rho power and all 0 I will take as a 0. Then what I get finally is like this. So I do this thing partly, rest you can do. I substitute f rho in above equation and try to simplify. This is the ready-made solution I have written. So I am copying from that, but you actually do it. If it is asked in the exam, examiner may seek your complete derivation in order to give you marks. So I believe that you will all do again. And since I have concentrated only on this rho raised to s plus 1 power, so I have done the differentiation with respect to that. All the constant term and the common term I have cancelled out, and finally what I'll get is this, correct? And in now next step, I will put the g rho value from this part, and then I will do the differentiation again. Again, you can see this is a second order differentiation, correct? So this rho raised to k term will give differentiation. First time when I do it will give k out, and then when I do it next time, that is k minus 1 out. And likewise, when I do this substitution here, finally what I'll get, that I am writing. I hope this is my pages are going in sequence. So I use this equation directly, and then I substitute the value of 0. Again I do this, and again I believe that you will do it your own. So on doing that, I have written it. So let me copy it directly. I am substituting the value of g, so which involves the sigma sign. Sigma sign I can write common for all the terms. That freedom is possible, is available. So I write like this. So what I have is like this. First time differentiation gives me k out, second time differentiation gives me k minus 1 out, and then ck, and then rho raised to k minus 1. Don't forget, there is already rho in it. So even after doing the 2-time differentiation, finally this rho will multiply whatever sigma is there that I have written commonly out, right? So this is the simplification which I am doing. For the second term, again, this 2s plus s minus rho, correct? Then k, because it's a one-time differentiation, so only k will come out, ck will come out, and rho raised to k minus 1 because the differentiation is done, and plus that last term that I will write lambda minus s minus 1 and ck rho k, because it does not involve, the last term does not involve any differentiation, so this 0 will be as it is written here, but this sigma sign from all the terms I have written commonly. So basically this is my final equation that I can write. And only thing which now we are doing here, because if I just open up this bracket, for example, if you just concentrate on this particular term, if I open up this bracket, it is 2s, sorry, this is 2s, whether here it is, here it is written 2, and here also it should be 2. This also indicates that one should not copy, rather derivation gives the correct way. So if I open up this bracket, so rho into k ck rho raised to minus 1, so it will give you rho k. You can see that. So if I combine this term, only this part, then the power of rho will be rho raised to k, and that rho raised to k term can be mixed with this, correct? So all the terms are now mixed according to their similar power. So in the next step, I will open up this bracket, 2s plus 2, one term, and this rho term I will merge with this part. This is the one thing I will do. Second thing what I will do is that here k is a dummy variable. It is just the dummy thing used to show the summation. Instead of k, I can take even p also, I can take r also. It is just to show that my summation is going from 0 to infinite. So if it is a dummy, then it also allows me to change, instead of k, we can write as a k plus 1. And that k plus 1, if I call as a k dash, then it is the same thing. So being a dummy variable, just to show the summation is going from the lowest possible value to the highest possible value, I can write k as a k or k plus 1. It makes no sense. So in the first term, correct, here I can write wherever is the k, I can write that as the k plus 1. So what happens here? I will write k as k plus 1. Not only here, here also after removing this row from this bracket merged with the last term, now for this part also, this I can write as k into k as a k plus 1. So doing this substitution, what I will get is sigma over, and then we know that my summation will change from summation will go from k equals to 0 to infinite. But now what happens by changing k to k plus 1? Here the power will be k minus 1 written as k plus k is written as k plus 1, so it will be rho raised to k. Here also it will be rho raised to k. So, and this is already in the rho raised to k term. So all the terms are written as a rho raised to k. But beware, be sure that the coefficients which I am now writing, ck, is no longer remain ck, it will be ck plus 1. Right? So let me write it and then we try to give the physical understanding of that. This k I write as a k plus 1. Here if I write k as a k plus 1, it will be only k. So what I have, k into k plus 1, the first term. Here 2s plus 2, as I've said, this row is already merged in the last. So 2s plus 2 as it is. And this k I am writing as a k plus 1, so it will come here. And what is common here? That both this ck term will be written as now ck plus 1. Correct? And you can see now in a row, when I write k is k plus 1, so it will be rho raised to k. Here also it is rho raised to k. This is already as a rho raised to k. So that rho raised to k term I write throughout common. And what is done here? You were having this lambda minus s minus 1 like this, and this row part which comes here, it will also be merged here. Correct? So what we will have, that row part I can merge. Row when goes with this, it will be rho raised to k, and this k is multiplying. So what I have is plus, in fact minus, sorry. So it will be minus. And of course the ck coefficient. Though this equation is entirely written for rho raised to k power, but the first term is giving contribution not from the coefficient ck, but its contribution comes from the next coefficient, that is ck plus 1. This entire equation which we have written is for arbitrary value of rho and arbitrary value of k. So for each k term this is also true. And if it is true for each k term, then there is, without summation also you can write like this. Right? So this equation which I have written in the curly bracket, that I am writing for the specific k. So what I will write is, it's like this. So k into k plus 1 plus 2s plus 2 k plus 1, this coefficient will be there, ck plus 1, and then this will be, if I take it on a say on a other side, then we know that it will be this minus minus I can change, so it will be k, and all other term which are negative becomes now positive. And if I take a ratio of this coefficients of the series and all other terms on other side, then what I'll have is ck plus 1 can be written as k plus s plus 1 minus lambda, and this part goes down, so it will be k, and simplification is possible, but let me first write it, k plus 1 plus 2s plus 2 k plus 1. And you can see here in the denominator, this k plus 1 can be taken common. So finally, what I get is this. It is k plus 1 common, and what you are left with is 2s plus 2 plus k. Don't forget this ck, here it is ck. So this coefficients ck and ck plus 1, they are in fact related with each other. If you know what is Ck, by substituting this all information, you get the next coefficient, that is Ck plus 1. In fact, that was the reason that I have assumed that your first value of coefficient, that is C0, should not be 0. Just to recall, you remember that I have assumed that C0 should not be 0. So what happens in the series solution technique, we always go in steps. Information of the previous step is now carry forward to find out the next step. For example, I start my series like that. What is C0 if I know? If I substitute C0 here, it will give me the information of C1. That C1 in the next cycle, in the next calculation steps is used here. It will give me the information about C2, and this carry forwards. So C2 gives information about C3, and therefore I can call this as my recurrence relation. So this equation number D is nothing but your recurrence relation. So what actually has happened? I think you might have lost the charm of learning the physics, and we are involved in the mathematics. So I start again with this. My first page, I just very hurriedly brushed through that. Our idea was to involve the potential in our Kg equation. And as a simplest example, we have involved the Coulomb potential, that any negative charge particle under the Coulombian force when performing any motion, then your kinetic energy will be written as the total energy minus potential energy. And then by substituting all this information and looking to the nature of the potential, that it depends only on the r part and not on theta phi part, has allowed us to separate your psi into radial and the angular part. And then by doing some simple mathematics, finally we obtained the radial equation. This radial equation is then in fact also turned into the dimensionless form by assuming certain quantities, and this radial equation in the dimensionless form is being now attempted to solve using the series solution technique. But before to start with any series to solve the problem, we should know its asymptotic behavior. So at a rho tends to infinite, what are the possibilities that we explore? And then we say that there must be some exponential damping term to take care of the finite probability or the zero probability at the infinite. And doing all this simple mathematics, eventually what we have developed is the recurrence relation. So if I just take these two equations and just look at these two equations together, if I know C0, I know C1, C1 gives me C2. So basically I can generate this series in a steps, starting with C0, then C1, and then C2, means your rho raised to 0, rho raised to 1, rho raised to 2, like that. So that term will be used here to produce your F. Once you know what is F, multiplied by this exponential function, it gives me capital R. Once you know capital R, you multiply it with the spherical harmonics Ylm theta phi, it gives the information about the psi. So your problem can be solved provided if we solve this recurrence relation. Correct? So basically we are now looking for a solution of this recurrence relation. How it can be solved, that we try to solve next. So in the next part, what we will do, we will try to solve this. But before we solve this equation, as we will discuss, that it is always advisable to look for the ready-made available series in the mathematics who have the similar kind of recurrence relation. Right? If you know that there is a resemblance of this series, this recurrence relation with any particular series, then it will reduce your labor, mathematical labor, because you already know the solution, you already know the series having the similar type of series recurrence relation, and we can directly adopt that series to predict or to estimate our solution. So that part we take the next. So in the next we will solve this, and obviously some inferences, more understanding about the Kg equation that we will derive. Up till we have mentioned in the previous talk that the Kg equation is basically the relativistic field theory or the equation which deals with the many body, many particle system. Some of them are positive, some of them are negatively charged particles. So it is a many particle systems. But what else? Is this the only property or the characteristics that one understand from the KG equation, or is there something more we can explore from the KG equation that we try to discuss in the next? So I hope you have enjoyed this lecture. As I've said in the beginning of this lecture, this entire topic is divided into two parts. In this first lecture, that is in the fourth lecture, in the first part we have derived the recurrence relation, and in the next lecture we will solve this recurrence relation under the certain conditions, and we try to conclude the physics of it. So I hope you have enjoyed, and obviously if you have liked, you can share and subscribe it, and obviously if you have any doubts, any queries, you can comment to our comment sections. Looking forward to you in the next lecture. Thank you.